In July 2025, astronomers spotted something moving through our solar system that didn't belong here at all. Not from around our sun, and not from anywhere inside our own solar system in the first place. It's only the third object of its kind ever confirmed in the entire history of astronomy. And what the James Webb Space Telescope found inside, it turned out to be genuinely strange. No fabricated signals are needed here because the real story is stranger than most people realize. Stick around, and if you want more real space science explained honestly, subscribe right now. Let's start with what this object actually is because the basic facts matter here first. On July 1st, 2025, a survey telescope called ATLAS spotted something unusual moving across the sky. Its trajectory didn't match anything that could naturally belong to our own solar system. Objects that orbit the sun follow curved, closed paths, ellipses that bring them back around repeatedly. This object was moving on a hyperbolic trajectory, a path too fast and too straight to be captured. That kind of trajectory means only one thing: it came from outside our solar system entirely. It passed through our neighborhood and is now leaving again, permanently, never expected to return here. It was named 3I Atlas, and the 3I designation means it's the third interstellar object ever confirmed. The first was Oumuamua in 2017, and the second was 2I Borisov, discovered back in 2019. 31ATLAS is the third, and astronomers worldwide immediately turned every available instrument toward it. Objects like this are exceptionally rare, and the window to properly study one is always brief. By August 2025, multiple observatories were already tracking it closely, eager not to miss anything. Hubble had already observed it, and so had the SPHERX observatory shortly beforehand as well. On August 6, 2025, the James Webb Space Telescope finally took its own careful turn. Using its near-infrared spectrograph, Webb captured its first detailed chemical look at the object. That instrument reads specific wavelengths of light to determine an object's exact chemical makeup. And almost immediately, something about the readings coming back from 3I Atlas simply didn't add up. Comets in our solar system have a fairly well-understood and predictable chemical signature already. As they approach the sun and warm up, ice inside them turns into surrounding gas. This creates a cloud called a coma, made of water, carbon dioxide, and other common compounds. 3I Atlas didn't match that familiar pattern at all when Webb's instruments studied it closely. Webb found it was unusually rich in carbon dioxide compared to typical solar system comets. A researcher working on the analysis flagged the finding immediately as worth digging into further. Being unusually rich in carbon dioxide doesn't imply anything artificial or unnatural about the object. It simply means this object formed somewhere with a very different chemical environment than ours. That difference likely existed billions of years ago, around a completely different and distant star system. That's exactly why scientists were so eager to study this object as quickly as possible. An interstellar object isn't just a passing curiosity drifting harmlessly through our cosmic neighborhood. It's a direct physical sample of material formed elsewhere in the galaxy, delivered to our doorstep. You normally can't access material like that without physically traveling to another star system yourself. 31ATLAS made its closest approach to the sun, called perihelion, back in October 2025. This is normally the best time to study any comet since solar heat vaporizes more material. That vaporization creates a brighter, more detailed coma that telescopes can analyze in greater depth. After that close pass, as the object began moving back toward interstellar space, data improved further. In December 2025, Webb turned its mid-infrared instrument, known as MIRI, toward the object again. This instrument captures a different slice of light, revealing signatures invisible to Webb's earlier instrument. What it found this time added yet another layer to the growing scientific mystery. Webb detected methane venting from the comet roughly 2 months after its closest solar approach. The amount of methane relative to water was surprisingly high compared to typical solar system comets. Combined with the earlier carbon dioxide findings, the European Space Agency described the pattern plainly. These ratios point toward a very different formation environment than most solar system comets experienced. In plain terms, this object was assembled somewhere with a completely different chemical recipe entirely. But the single biggest discovery from all of this research was actually still coming later. Researchers didn't stop at simply measuring carbon dioxide and methane levels inside the object. They also studied isotopic ratios, specifically looking at carbon and deuterium, a heavier form of hydrogen. These isotopic ratios work almost like a permanent chemical fingerprint left behind at formation. Depending on stellar activity happening in that region of the galaxy at the time, ratios lock in. By measuring those ratios carefully, researchers could estimate roughly when and where the object first formed. The results, published in the peer-reviewed journal Nature on June 22, 2026, were hard to believe. 31ATLAS appears to be somewhere between 10 and 12 billion years old, an enormous span of time. For context, our own solar system is only roughly 4.6 billion years old by comparison. This comet is potentially nearly 3 times that age, formed long before our sun ever existed. It likely formed during an early, intense period of star formation inside the Milky Way galaxy. Think about what that actually means for an object we can now directly study up close. This object drifted through interstellar space, completely untouched, for far longer than Earth has existed. It formed around a different star, in a different region of the galaxy entirely long ago. That point in cosmic history sits closer to the Milky Way's birth than to our own. After billions of years of silent travel between star systems, it finally passed close to our sun. That gave us a brief chance to notice it, study it, and understand where it came from. Because it's on a hyperbolic trajectory, 3I-ATLAS will never return here again after this pass. This is our one and only chance to study this particular object directly and thoroughly. Once it exits the solar system for good, it's simply gone, beyond any telescope's future reach. It's worth addressing something directly here, since it came up almost immediately after discovery. Online speculation quickly suggested the object might not be a natural comet at all. Some suggested it could be some kind of artificial spacecraft sent from elsewhere in the galaxy. The overwhelming consensus among astronomers studying the actual data says otherwise, clearly and consistently. 31ATLAS behaves exactly like what it appears to be, an ancient but entirely natural comet. Its brightening and dimming near the sun, its outgassing, its trajectory, all fit known cometary physics. The genuinely remarkable part isn't that it's artificial, but that it's this astonishingly old and intact. Material formed under conditions this different happened to drift close enough for detailed human study. So why does any of this actually matter, beyond simple curiosity about one unusual visitor? Interstellar objects like this are one of the only ways to directly sample other star systems. You can't send a probe to another star system with today's available propulsion technology. It would take tens of thousands of years just to physically reach another nearby star. But when a piece of that system drifts through ours, it brings a sample directly here. Every measurement of its chemistry becomes a data point about conditions somewhere else entirely. Oumuamua gave scientists their first ever glimpse of this kind of object, but only briefly. It was small, faint, and gone before most instruments could get a proper detailed look. 2I Borisov behaved much more like a typical comet, giving useful but less surprising data overall. 31ATLAS is different, since it's old enough, active enough, and was tracked by many major observatories. Hubble, SPHERX, and Webb all contributed, building a genuinely detailed chemical profile of the object. That's an extraordinary scientific opportunity, and it explains why research teams move so quickly. There's also a broader question this discovery feeds into about our entire surrounding galaxy. How common are objects like this one, actually throughout the wider Milky Way galaxy? Astronomers have long suspected interstellar objects pass through our solar system more often than detected. Most are simply too small, too faint, or moving too quickly for current telescopes to catch. Finding 3 confirmed interstellar objects within less than a decade suggests they're more frequent than assumed. With newer, more sensitive survey telescopes coming online in the years ahead, detection rates should rise. These future telescopes are built specifically to scan large areas of sky repeatedly and quickly. Astronomers expect to start finding interstellar visitors more regularly, rather than treating each as rare. That shift matters enormously for how researchers study material from beyond our solar system going forward. Instead of waiting years between rare discoveries, this could become a genuinely active field of research. So here's where things actually stand with 3I-ATLAS as of right now, in simple terms. It has already passed its closest approach to the sun and is now heading back outward. It's on a trajectory that will eventually carry it beyond the reach of any current telescope. Before it goes, it left behind a body of data that researchers are still actively analyzing. That data includes unusually high carbon dioxide content and unexpected methane venting from deep inside. It also includes isotopic ratios pointing to an age of roughly 10 to 12 billion years. That makes it one of the oldest individual objects ever directly studied by human instruments. It formed in a part of the galaxy vastly different from our own solar system entirely. That formation happened during an era of intense star formation long before our sun existed. It then spent billions of years drifting silently through space, completely unobserved by anyone at all. Until it happened to cross paths with a curious species of primates pointing sensitive telescopes skyward. That's the actual story here, with no fabricated signal, no secret course correction, no hidden cavity. Just an ancient, entirely natural piece of another star system, passing through ours for the first time. Perhaps the most remarkable implication isn't really about this single object on its own merits. It's about what discoveries like this reveal regarding the wider structure of our entire galaxy. For most of human history, every comet and asteroid scientists examined came from our own system. Now, for only the third confirmed time ever, we've directly studied material from another distant star. That changes the scale of questions astronomers can finally ask using real observational evidence. Instead of studying only our local cosmic neighborhood, researchers can compare entirely different planetary systems. Each new interstellar visitor becomes another opportunity to understand how typical our own solar system really is. Did carbon-rich comets commonly form around other young stars, or is this chemistry genuinely unusual? Did distant planetary systems experience similar early histories, or did each evolve along completely different paths? Objects like 3I Atlas provide physical evidence instead of assumptions, replacing speculation with careful measurement. Every interstellar object effectively acts like a messenger carrying preserved information across the galaxy. Unlike spacecraft, these travelers weren't intentionally sent, but they still transport valuable scientific clues regardless. Each measurement made today tells researchers something about environments that may no longer even exist. Many stars surrounding 3I Atlas during its formation have almost certainly evolved significantly since that ancient time. Some may have expanded into red giants, while others have already exhausted their fuel entirely. Yet this remarkably small object continued drifting almost unchanged, quietly preserving evidence from long ago. That's exactly why researchers pay such close attention to isotopes rather than surface appearance alone. Isotopic ratios often preserve the original fingerprint of an environment that existed before our sun formed. Reading those signatures requires extremely precise instruments, but they reveal histories no other method can. In many respects, studying 3I Atlas resembles investigating an archaeological artifact from another planetary system. Its chemistry records events from billions of years ago, long after its birthplace changed completely. Every successful measurement adds another small piece to an extraordinarily ancient galactic story being told. These interstellar visitors also remind us that planetary systems aren't isolated islands separated by empty space. During planet formation, powerful gravitational interactions regularly eject asteroids and comets beyond their home systems. Instead of remaining nearby, they become permanent travelers wandering silently between stars for immense stretches of time. The Milky Way may contain staggering numbers of these ancient travelers moving through space right now. Most never approach our solar system closely enough for telescopes to detect before disappearing again. Only a tiny fraction ever passes near enough for astronomers to properly observe and study. That means every confirmed detection carries significance extending well beyond that individual object's own characteristics. Each discovery helps estimate how many similar visitors might exist throughout the galaxy, undetected so far. As more observations accumulate, scientists can gradually refine those estimates with increasing overall confidence. Future observatories are expected to transform this by scanning far more of the sky, far more often. Rather than finding one interstellar visitor every several years, astronomers may soon detect dozens regularly. That shift alone could completely reshape this emerging field of astronomical research within coming decades. Instead of treating every discovery as a once-in-a-lifetime event, researchers could start spotting real patterns. Patterns in chemistry, structure, composition, and age would become far easier to recognize with larger samples. Only then will astronomers know whether 3I Atlas represents something typical or something genuinely unusual overall. Several space agencies have already explored mission concepts designed to intercept future interstellar visitors directly. The greatest challenge isn't distance alone, but extraordinary speed, leaving little time to prepare a spacecraft. Engineers therefore envision missions waiting in advance, ready to launch quickly when a visitor appears. A successful interception would let humanity photograph an interstellar object from close range for the first time. That achievement would represent another historic milestone in understanding the wider galaxy around our solar system. Until then, telescopes remain humanity's most powerful tools for studying these incredibly rare cosmic visitors. Observatories worldwide combined visible light, infrared observations, and precise orbital tracking into one detailed investigation. No single telescope could have produced such comprehensive results without cooperation across many research institutions. That's ultimately what makes this story compelling without requiring dramatic speculation or unsupported claims online. Reality already provides something astonishing. An ancient object formed before our sun, briefly visiting our corner of space. Sometimes the universe proves far more extraordinary through verified science than through invented mysteries or sensational headlines. 31 ATLAS is already leaving our solar system, continuing a journey that began billions of years ago. Its visit lasted only a short time, but its scientific legacy will influence research for years ahead. And perhaps someday, another ancient traveler will arrive carrying an entirely new chapter of this story. If you want to keep following what researchers find as they continue analyzing this data, subscribe now. Turn on notifications because the real universe keeps turning out to be strange enough on its own. It never needs anyone to invent anything extra to make it worth paying close attention to.